This is AI Paperslop, and today we are looking at Draw2Think, harnessing geometry reasoning through constraint engine interaction.
Right, and to give you the core insight straight away, vision language models like Gemini and GPT, they're getting way better at math, but their intermediate reasoning states are completely unverifiable.
Yeah, like visualizing an auxiliary line or, an 89-degree angle. That all happens in hidden latent tokens.
Exactly. Draw2Think solves this by taking a frozen VLM and wrapping it around a deterministic constraint engine, specifically GeoGebra, using a proposed draw-verify loop.
So the VLM proposes an action, the engine executes it algebraically, and feeds exact measurements back.
Yep. By externalizing these hypotheses onto a constraint-checked canvas, it dramatically improves accuracy on complex 3D geometry, up 16.4% actually.
Wow, 16%. And it also completely crushes text-to-image models in generating diagrams, right?
Oh, absolutely. It even proves that some standard math benchmarks have incorrect answer keys.
Which is wild. So if you are listening to this, think about an architect trying to build a 100-story skyscraper entirely in their head, just hoping the physics work out when the concrete pours.
That is pretty much how today's top VLMs do math.
Right. But Draw2Think is like giving that architect a CAD system that rigorously checks the math after every single drawn line.
Which is a huge paradigm shift. Because if we look at why previous attempts to fix geometry reasoning failed, it really comes down to how we measure progress.
Yeah, the end-to-end outcome accuracy problem.
Exactly. Right now, you feed the model an image, ask a question, and check the final number. But geometry requires multi-step deductive reasoning.
Right. I mean, intermediate steps like deriving the length of one obscure hypotenuse, those become the absolute premises for later steps.
Yes, and if the model hallucinates that one length, the entire foundation just crumbles. But tracking end-to-end accuracy conflates everything.
It lumps together perception, construction, and deduction. You never really know where the model went off the rails.
Which is super dangerous when you remember it's all happening in latent space. I mean, on a screen, an 89-degree angle and a 90-degree angle look identical in pixels.
Yeah, a neural network is just estimating a pixel grid, so it treats them as the same thing.
But mathematically, they represent entirely different universes. One is a right angle unlocking dozens of specific theorems, and the other is just a slightly bent line.
So researchers have tried externalizing this before, but why do the existing fixes miss the mark? Like formal provers certify proofs, don't they?
They do. Things like alpha geometry are incredible. But they only certify the logical steps, not the specific messy visual measurements that benchmarks rely on.
And then there are things like Math Canvas or Visual Sketchpad.
Right, but those basically just draw a sketch and force the model to look at it. You are still relying on a visual estimation of a pixel grid.
There is no exact mathematical guarantee, but I have to push back a bit here because we already have code generation fixes.
You mean like generating Python scripts?
Yeah. Models generate Python scripts with Matplotlib all the time. Why isn't that enough to get a mathematical guarantee? You're relying on code, not pixels.
Well, that really comes down to when the verification happens. Generating a Python script, like in ggbench, is post-hoc.
Oh, meaning it happens after the fact.
Exactly. The model writes an entire 10-step script in one go, executes it, and then checks the geometry.
So if step 2 was mathematically impossible, like a triangle with 2 obtuse angles, it doesn't find out until step 10.
Right, the code just crashes at the very end.
So you can't fix a crooked wall after the roof is already nailed down?
That is the perfect analogy. The missing piece that Draw2Think brings is per-action verification.
Okay, so it stops the model the exact moment it makes a mistake.
Yes. It creates a verifiable intermediate state that is executable, checkable, and revisable mid-thought.
Let's break down the architecture of this proposed draw-verify loop. How does it enforce reality without breaking the AI's flow?
Well, it treats geometry as a state reachability problem. It gives the VLM an action space of 92 typed tool specs.
Typed tool specs, like specific commands.
Yep. Hard-coded commands like add perpendicular line or query angle. The loop starts with propose.
Where the VLM makes a decision based on natural language descriptions.
Exactly. It uses a frozen model Gemini 3 flash preview, in this case, so it relies entirely on pre-trained knowledge to select a tool.
So it looks at the problem and says, based on what I know, I need a perpendicular line here.
Right. Then comes the second step, draw. GeoGebra takes over, using the GAC computer algebra system and Grubner basis elimination to execute it.
Wait, Grubner basis elimination? You can't just drop a term like that. What is the engine actually doing there?
Fair enough. So normally we plot things with approximate coordinates, right? Like
Yeah.
x equals 2 point something.
Yeah, standard graphing.
A computer algebra system abandons coordinate guesswork completely. It turns geometric rules into pure algebraic equations.
Oh, wow. So a line isn't a series of dots, it's a fundamental formula.
Exactly. Gröbner basis elimination is just an advanced method for solving those massive systems of polynomial equations.
Okay, that makes sense. It enforces relationships algebraically.
It locks in undeniable mathematical truth, which leads to the third step, verify. The engine hands back a structured observation.
Like an exact scalar value or an object delta.
Or an explicit rejection.
But wait, what happens if the model proposes something that algebra won't allow? Like hallucinating three 90-degree angles in a triangle? Does the system just crash?
No, and that is the elegance of this asymmetrical loop. The VLM guesses, but judgment is fully delegated to the constraint engine.
So the engine explicitly rejects it and throws an error.
Yes, but it only rolls back that one local failed action. The rest of the valid canvas is perfectly preserved.
Oh, I see. It's like having a math tutor who stops you the second your pencil writes something wrong but leaves the rest of your page intact.
Exactly. You don't start from scratch. You just engage in state-preserving replanning based on the error message.
Because of that loop, the researchers separated accountability into two auditable properties, right?
They did. Today, when an LLM fails geometry, we don't know why. Draw2Think splits the blame. First is construction fidelity at the model level.
Did the VLM actually build what the problem asked for?
Right. And tested on the GeoGebra benchmark, it hit a 95.9% predicate level pass rate.
Which means it got the individual rules correct almost 96% of the time, like making line A parallel to line B.
Yep. And on a strict problem level pass rate, meaning the whole shape had to be perfect, it hit 84% under an engine exact verifier.
That is massive validation. And the second property is measurement faithfulness, right?
Operating at the engine level, yes. Are the returned measurements exact? Since GeoGebra uses algebraic relations, queries return deterministic flawless values.
This totally changes evaluation. I mean, traditional LLM as a judge is basically a police lineup.
Oh, how so?
You look at the final answer, you look at the image, and the judge makes a holistic, vibe-based guess if the model got it right. But Draw2Think is a DNA test.
I love that. The constraint engine doesn't guess. It proves exactly what failed. And that DNA test reveals two distinct failures we normally conflate.
Structural errors and precision errors.
Right. Structural errors happen when the VLM builds the wrong shape entirely. The researchers found these are heavily concentrated in angle expressions.
And precision errors are when the model builds the right shape but hits float 64 coordinate limits, right?
Exactly. Floating point limits dictate how computers represent decimals, usually tapping out around 16 decimal places.
So if it calculates a square root and uses that exact decimal in 50 steps, rounding errors compound. By step 50, the lengths are ruined.
And a standard benchmark just marks both failures as wrong. But Draw2Think stores the exact algebraic concept, so the precision error never happens.
We can finally see what the model actually misunderstands versus what's just a calculator limitation. So you'd assume it aces every test now.
You would think so.
Right.
But the impact is surprisingly selective.
Yeah, the researchers tested 10 benchmarks using Gemini 3 Flash Preview. And on visually grounded tasks like MathVerse and GeoSketch, accuracy went up by 4.1%.
Because exact external measurement replaces expensive latent simulation.
And on the officially hard 3D split, Solid Geo Hard, it jumped an unbelievable 16.4%.
But here's a catch. On standard textbook benchmarks, PGPS 9K and Geo 3K, accuracy actually dropped.
Which is wild to me. You hand an AI a perfect calculator and it gets worse at textbook math. Down 4% on PGPS 9K.
It reveals this fascinating paradox called cognitive offloading.
How does that work?
Well, on textbook benchmarks, frontier VLMs have incredibly strong internal priors. They've processed so much data, they practically have those problems memorized.
Oh, I see. So forcing the model to stop, translate the question into 92 different tool specs, and construct it step by step just adds overhead.
Exactly. Unnecessary execution overhead. Every tool call is a new opportunity to make a syntax error or trigger a cascade failure.
So if it already knows the answer internally, the tool is a liability. It's like asking a career mathematician to prove 2 + 2 using formal set theory.
Right. They can do it, but they're more likely to make a clerical error writing a 20-page proof than if they just yelled out 4.
So engine grounding is only valuable for real visual or spatial ambiguities. Knowing that overhead exists makes the ablation studies crucial.
Definitely. We have to dissect this 92-tool arsenal to see what's actually doing the heavy lifting.
So they systematically took tools away. First, they removed the query tools.
The explicit commands that ask the engine to measure an angle or calculate a length, accuracy dropped 4.2 points, obviously.
But the VLM's adaptation was the most fascinating part of this deep dive. Deprived of query tools, it didn't just give up.
No, it started relying on construction returns.
Which means it realized that using a tool like addAngle automatically spits out the exact measurement as a side effect.
Right, so the model hijacked the construction tools. It wasn't building new geometry, it was forcing the engine to measure things for it.
It's an amazing display of emergent agentic behavior. It reminds me of a mechanic whose high-tech scanner gets taken away.
Oh, so they just start listening to the engine belts.
Exactly. They turn on the AC and listen to the belt squeal to reverse engineer what's wrong with the alternator.
Yeah.
The VLM just creatively hacked the remaining tools.
Such a great analogy. And now, when they took away the delete tools, overall accuracy barely dropped.
Really? Why is that?
Because the delete function is mostly a heavy rollback mechanism for total strategy resets.
Ah, so the standard reject and replan function where the engine just throws an error and lets the model try again handles the minor errors.
Yep, it's robust enough on its own.
What about the semantic layer, like the actual English descriptions attached to the tools?
When they strip the natural language out, leaving just bare function signatures, the rate of LLM bypass jumped 4.6 times.
Just to clarify, what does LLM bypass look like in practice?
Without a description like use this tool to find the perpendicular bisector, the model just sees raw code, like tool 42.
Oh, so it just gets confused by the lack of context.
Exactly. It decides the external engine is too much effort, completely bypasses it, and reverts to guessing the final answer from memory.
Proving it desperately needs that semantic guidance. The English descriptions bridge the latent reasoning into mathematical syntax.
And that bridge leads to what I think is the ultimate flex of this paper.
Oh, the mathverse anecdote.
Yes, because the best proof of a system isn't passing a benchmark, it's proving the benchmark itself is flawed.
Right. So on a visual-only area problem with two intersecting circles, you have to calculate the overlapping sectors.
The baseline VLM looked at it, ran its internal simulation, and answered 1.0.
Which perfectly matched the official ground truth answer key.
But Draw2Think systematically constructed the circles in GeoGebra, calculated the sectors algebraically, and insisted the answer was 7/6.
Which is roughly 1.167. So when a machine stubbornly disagrees with the official key, you do a manual human audit.
They checked the math by hand and realized Draw2Think was right. The benchmark was mathematically wrong.
The baseline VLM only got the quote-unquote correct answer because it hallucinated the exact same flawed visual intuition as the human creator.
It is incredibly sobering. If you evaluate purely on latent spatial simulation, you are often just comparing two flawed guesses.
And declaring the match as truth. It's wild. Now, this mathematical rigidity also unlocks diagram generation, right?
It does. Tested on GenExamMath for rendering diagrams from text, it scored 68.2 strict and 90.5 relaxed.
Which completely crushes standard text-to-image models. FLUX and OpenAI native didn't even come close.
It's funny to think billion-parameter image models failed to draw a simple tangent line.
But it makes sense given their architecture. Standard text-to-image models are diffusion networks. They treat math like an art project.
Guessing what a tangent line looks like based on pixel probabilities.
Right, whereas Draw2Think treats art like math. It plots an undeniable algebraic reality. It's drawing what's mathematically true.
Zooming out from geometry, Draw2Think is a massive proof of concept for the future of AI agent design.
If you are an engineer listening to this, the major takeaway is that inference time operation against an exact external engine changes how a model thinks.
You don't necessarily need a smarter model with a trillion more parameters.
You need a model interfacing with an unforgiving environment that immediately corrects structural hallucinations before they compound.
We are shifting the burden of proof. We're moving from models that confidently talk about math to agents that actually do the math in an audible workspace.
And I want to leave you with this final thought to chew on. Think about the data being generated here. Every trajectory creates structured, step-by-step signals.
Explicit accept and reject flags for every single construction attempt.
Paired with exact algebraic values. That is a goldmine of process-dense reward data.
Right now, Draw2Think operates as an inference time tool.
But if we capture these trajectories, how the model learns to hack the system, recover from errors, build perfect 3D geometry, could this become the ultimate automated synthetic data generator?
We could use this exact data to fine-tune the next generation of reasoning models.
It could be the bridge from clever inference time hacks to native training time brilliance, where models internalize the strict logic of the engine itself. Imagine what an AI trained purely on mathematically verified trial and error could build.